Hello, this is question 6 from the 2018 MAT. A positive rational number q is expressed in friendly form if it's written as a finite sum of reciprocals of distinct positive integers. For example, 4/5 is a half plus a quarter plus a 20th. Okay, express the following numbers in friendly form. 2/3. Okay, that's an easy one. We do that one quite a lot. A half plus a 6. 2/5. Right, that's not as easy. What can we do there? So if it was 4/10, would that help? If we had a tenth, but then we're stuck with 3/10. If we got 3/10, we'd have to do another tenth. So that isn't going to work. But if we went to 8/20, that could be all right, couldn't it? Because we could do what could we do with that? We could do a 20th, would leave us with 7. If we did a tenth, then that'd leave us with 4. So, 5. So that would leave us with a quarter. Is that right? So we'd have 5/20 plus 2/20 plus 1/20 is 8/20. Right, okay, that was a bit fiddlier. And then 23/40, that's just going to drop out, is it? Because we could do 22 and 1. Yeah, so let's do that then. So a 40th plus a 20th plus a half. Okay. Right, I got a feeling they're going to be wanting us to find a pattern of how to actually do that rather than just stabbing in the dark, but let's deal with that when it comes to it. Part 2, let q be a rational number between 0 and 1. M be the smallest natural number such that 1/m is less than or equal to q. Right, okay, the smallest natural number such that 1/m is less than or equal to q. So the largest one of these fractions that we can pull out. Maybe that was the method that we were using here. So yeah, half is the largest reciprocal integer you can pull out of 2/3. Same here with the bottom one, and then we got a quarter there for that one. So, well, I could have taken a third out of there, couldn't I? Yeah, okay, so anyway, we'll see. Suppose q is a over b, q minus 1/m is c over d. In the lowest term, show that c is less than a. Good Lord, right, that is a lot to take in. So we've got some number q between 0 and 1. So 1, 0, so that's q. Okay. Then we've got m, the smallest natural number such that 1/m is less than or equal to q. So say we've got some other number here then. So that's our 1/m. That's the smallest natural number. So we're going for, so if m was 1, we're just getting 1. And then we might go m is 2, would then drop below it. Or if q had been down here, then it wouldn't do, and then we do another one, and we keep on going down and down. So q is either going to sit on 1/m, that's our equals, or it's going to be between 1/m and 1/m minus 1. Okay, I'm a bit out of scale now on this, but obviously we go to half would be the first one when m is 2. Suppose q is all of those things, and we have to show that c is less than a. So we've got q is a over b. So q is greater than or equal to 1/m. So that's a over b is greater than or equal to 1/m. We certainly want to get a in there because we need a to be in an inequality. And q has to be less than 1/m minus 1. So we can put that there as well. So that's good. And this one looks like it might be more useful because it doesn't have an equal sign in it, and we don't want an equal sign in the answer. So maybe that's what we want. I don't know. Let's put the other equation down then. So a over b minus 1/m equals c over d. Right, that's just our second one of these equations that they've given. There's certainly similarities between this bit here and this bit here because we've got a's, b's and m's. So let's try getting these on the flat a little bit. So we're saying a m minus b over bm is equal to c over d. So we've got that, and we've also got that a m minus 1 is less than b. Right, how does that help? am minus a, yeah, we can manufacture an am minus b out of this. am minus a is less than b, so am minus b is less than a. Right, we've got the a on its own on the right side of an inequality here. So this thing is less than a. So that means we've got that a over bm is greater than c over d. Right, so that's sort of there, except we've got a bm and we've got a d. And we've got no way of getting rid of that d because it's the only place it turns up. So how do I use, what are we doing? Suppose that is that. Suppose q is a over b, q minus 1 over m equals c over d in their lowest terms. Right, so if these are in this thing here, and if this is if in lowest terms, then bm is going to have to be equal to d. Otherwise, they're not in lowest terms. If these things are the same, we must have the same number top and bottom on both of them. So am minus b would have to be equal to c, and bm would have to be equal to d. So we're fine. And then we can go in there and say, therefore, a is greater than c. That was horrendous for a second part of a question. That was really difficult. Part 3, suggest a procedure by which any rational q with q between 0 and 1 can be expressed in friendly form. Use the result in part 2 to show that this procedure always works, generating distinct reciprocals and finishing within a finite time. Right, so we've got to use this result of, well, the thing they're doing is chopping off. They're chopping off the highest possible amount. It's the largest reciprocal. So that's what they're telling us in part 2. That's what they've led us to do. So let's say then remove largest possible reciprocal each time. So that means then we're going from q equals a over b, and then we're going to go to c over d for the new one. So this will be like q prime will be c over d. So we're doing that, and we know that c is less than a. So how does that help? C is less than a. So we're decreasing the numerators each time. So eventually we got to hit 1. So, right, okay, yeah, that's going to be it then, isn't it? Right, so we remove largest possible reciprocal each time. So why must it finish in a finite time? So this will finish in a finite time because the numerator is reducing each time. Brackets, so process ends when the numerator equals 1. Actually, is that guaranteeing we got distinct? Generating distinct reciprocals, finishing with finite time. So, well, we must be getting something smaller, mustn't we, each time? Is that? Otherwise, yeah, because that's not complete what I've put down here. So we're chopping off a chunk. We chop off a half, say, just as an example. So we've got some number then. If q was between a half and 1, we chop a half off. We must have something less than a half because we just chopped off the biggest bit. and if we've chopped off the biggest bit, then we must get a smaller amount next time. We don't really have any choice, do we? So if we have removed largest reciprocal, the next reciprocal must be smaller. Must be smaller. Therefore, will be distinct each time. Right, okay. Yeah, the distinct bit was a little bit tricky. Demonstrate your procedure by finding a friendly form for 4/13. Right, new sheet then. So 4/13. What is the biggest bit that we can take off of 4/13? So 4/13 is, well, that's more than a quarter, isn't it? Yes, that's more than a quarter. It's less than a third. Yes, yeah, because a third would be 4 1/3 to take us up to 13. So that is less than a third, and it's greater than a quarter. Certainly what we got there, isn't it? So if we've got that, then so we're going to have to do 4/13. We take off a quarter, then minus a quarter. So that's a mess already, isn't it? So that's going to be 52. We want each one of these over. So that's 16/52 minus 13/52. So we've got that now that 4/13 is equal to a quarter plus 3/52. Right, 3/52 then is less than a 17th, because 3/17 are 51, and it's more than an 18th because 3/18 are 54. So we need to do an 18th off of this then. So that is a quarter plus an 18th plus something else. So we've got to do, good Lord, 18, and so 3/52 minus 1/18. So, God, what a mess this blinking thing is. 1852. So we've got, well, 50 18s is 900. So we've got 936. And then on this side, we're going to have 3 18s is 54. And then we've got 52 there. So that's 2/936, which is 1/468. Wow, okay, right, well, it worked. So I've demonstrated the procedure. Assuming that the sum from 1 to n of 1/n, right, increases without bound as n becomes large, show that every positive rational number can be expressed in friendly form. Every positive rational number can be expressed in friendly form. Right, okay. Assuming that the sum of that 1/n increases without bound. Right, so we're talking about 1 plus a half plus a third plus a quarter, etc. So we've got every positive rational number. So we're saying we've got some value here, q, which could be anything. It's not between 0 and 1. This increases without bound. So we're going to be adding these up until we get to some value. So you keep increasing, yeah, we've got to keep increasing n until we get past. How is this going to work? We have to keep on increasing until we get past it. So then what do we do? And then we have to subtract. I mean, it's doing this every positive rational number. Wowzers. Right, this seems Yeah, this just seems crazy, but clearly we're doing this. We're increasing this. We're summing up. So this is going to be where we sum to n. This is going to be where we sum to n plus 1. We've got some value here, q, which is in between. So we increase n until the sum, we got that q is going to be between, is going to be greater than or equal to the sum from n equals 1 to n of 1 over n, but it's going to be less than the sum of n equals 1 to n plus 1 of 1 over n. So it's between those values. And it's saying we can do that because you can just keep on increasing without bound. Right, okay, so that's the sum of all of those things. So what do we do then? We then subtract that amount. So that this gives us, so this is a friendly form. Both of these things are friendly form. So that is in friendly form. So that's fine so far. Then we can say, so then subtract this sum from n equals 1 to n over 1 over n from q. That gives us q prime. So we've taken, which must be rational, because we've done, well, q minus that sum. We've done a rational minus a rational. Rational minus rational. So we've got that. So now we've got a smaller number. And yeah, so that'd be fine, wouldn't it? And then we can just keep doing it again. That is in friendly form because they're all distinct. So they're all reciprocals and distinct. So it must be friendly. I think we're here then. So q prime is less than q. So we can then, yeah, but are we going to get distinct? If we do this again, are we going to get duplicates? This is a distinct thing coming back in again. So what could we do on this? Are we going to get a problem of when we go up to the next one? So say we just add, because we're adding on something smaller next time. Just wondering how this is going to work, that we've gone up to, like say we've done 1 plus a half plus a third plus a quarter. So we would be adding on a fifth next time there, but it's not, that would go past it. Oh, well, if that's going past it, we have to end up being distinct, don't we? Because Q is going to have to be in between. We can't use any of these again, because if we could remove a quarter, we would have been able to remove a fifth. Right, okay, so that's what we need to put in. So the distinct bit does come in again. Repeat for Q prime, and then we can say that increases without bound. Show that every positive rational into, yeah. So we repeat for Q. Yeah, they put that in an interesting way. We because we're not actually doing it that way, are we? We're dropping down. We're not always including 1 in there. But still, we do this. Increase n until, yeah, so that's if it's greater than 1. Right, okay, I know I'm going around a bit in circles here, but it takes a while to put this together. So that is if Q is greater than or equal to 1, then we do this. If it drops below 1, so whatever's left here, yeah, the Q dash must be less than 1. So yeah, so we've got that if Q is greater than or equal to 1, where this must be then that Q dash is less than 1. So we can then say we don't want to repeat for Q dash. So for Q is less than 1, we've already shown it works. It works in friendly form. So we've dealt with that. The only thing we have to convince of is that we don't get a duplicate distinct value. So we can say here then that the friendly form of Q dash, this is the bit that I was getting at before about this, well, if we could have added on a fifth, then we would have done. So we can't end up duplicating that quarter. So friendly form of Q prime will have distinct, I'm going to run out of space here, but anyway, distinct reciprocals, because if we could have added on, how do we actually put this into words? The largest, so because the largest reciprocal must be less than 1 over n plus 1. Otherwise, we would have added it onto the first sum, else in first sum. Okay, you might want to put that into more of a sentence. So what I'm saying there, just to make that super clear, because it took me a while to cotton onto that. So if we're adding up this 1 plus a half plus a third plus a quarter, and then we stop because Q is sitting between that and adding on a fifth. And then we say, okay, fine. We've set that up. We've got a friendly series for this first part of defining Q. As in we got 1 over 1, 1 over 2, 1 over 3, 1 over 4. So that's friendly. We subtract that off of Q in order to get Q prime. But what's left for Q prime has got to be less than a fifth. Because if it was more than a fifth, we would have added a fifth on in the first place. It would have been in our first sequence. It will be in the first sum, as I've said down here. So when we then work out what's going to be going on with Q prime, which we know is going to finish in a finite time because we've done this in part 3, but it's going to start off with the largest possible fraction being less than the smallest fraction of the first series. So we can't end up getting any duplicates. These are all going to be distinct reciprocals. So yeah, this certainly gets split out into 2 bits. This is how this first process of increasing this n, this is to reduce Q down to a number between 0 and 1, which is where part 3 then kicks in. So we're reducing it down to that by chopping off all of these bits. And then what's left is just smaller and won't overlap with anything that we've done before. Right, that was difficult. Again, this paper's got so many difficult questions in. This is a tough year, 2018. A lot more difficult than 2017, that's for sure. So interesting question though, but very, very difficult. That last part, having to deal with these distinct values is tricky to say the least.